Alright, welcome back. Another installment of physics today. We've got text problem 15-101, a suggested problem for lesson 22. Alright, so let's get into it. We have a mass, looks like we have a horizontal spring, there's some displacement going on, and we have some time information with some speed of the block. And let's see, we're looking at some frequency here. Alright, based on this, I can guess that we probably have a simple harmonic oscillator type of problem. Alright, so that's going to play into our physics step, but let's get a better visualization of the problem by doing our drawing. Alright, so here's the drawing I put together. We have our mass here in the middle. It is at time 0, and it is currently at a position of x is equal to 0. It does have some velocity, so it's 5.2 meters per second traveling in the positive x direction, where this is my x-axis and this is my y-axis. So traveling in the positive x direction, and sometime in the future our mass here will get to this position, and that will be at a position of x is equal to x sub m, standing for the maximum, which will be the maximum amplitude of our oscillator, or our block and spring system. Alright, now as we look at our givens, we are given our mass here, our spring constant, and we're given the velocity. Now notice that I have my velocity in terms of my position at x is equal to 0 and at a time t is equal to 0. So it's at this point right here where it is passing through the equilibrium position, and at some time greater than t is equal to 0 it will continue on into the positive x direction and at some point reach the maximum amplitude. Next, we're going to make an assumption here. We're going to assume that our block and spring system is in simple harmonic motion, meaning that there are no losses along the way, that our block here will oscillate between the maximum positive amplitude and a negative amplitude, which is of the same magnitude. So it will oscillate back and forth between those two positions, passing through the equilibrium point until the end of time. And that pretty much summarizes what simple harmonic motion means. Now as we look at our tasks, we have 3 of them. First one is to calculate the frequency of our simple harmonic motion here. The next is to calculate the maximum amplitude in the x direction. And the next one is to write out the position function, which is dependent on time, for our mass and spring system. Alright, so as we head into our physics step, this is where you take out your scratch piece of paper, a blank printout of the problem, or whatever you have to write on, and pause the video and write out the physics equations you think you might need for a problem about simple harmonic oscillation. Alright, so how'd you do? Well, hopefully you have what I have. If you don't, then we'll have some time to talk about it. So our first equation here is relating our angular frequency with our period, and then again relating our angular frequency to our regular frequency. So script F represents the frequency of motion, whereas omega, that's not a W, that's an omega, represents the angular frequency. One is measured in radians per second, the other is measured in hertz, or cycles per second. So there is a difference between the two as far as units go, but they describe essentially the same thing. The next is our angular frequency, being a function of our spring constant and the mass connected to our spring. You may remember from lab number 5, for those that have already taken it, that if we want to slow down a block accelerating due to a spring force, then all we have to do is add mass. Well, here's where that comes into play. And we'll actually be able to pull out not only where that comes from, but how we can get at this third equation, which is the time-dependent position function for our simple harmonic oscillator, where our first term is the maximum amplitude, and our second term here is a sinusoidal function that will give us our simple harmonic motion. Inside of our cosine function, we have our angular frequency times time plus some phase constant. Okay, so let's move on to the solve step. Alright, we're now into the solve phase. We have our problem set up, so we're ready to go. So for part A, we need to find the frequency of oscillation. Well, from our physics step, we listed out our equation. Our angular frequency is equal to 2 pi times the frequency. And we're looking for this f here, not the angular frequency, but the regular standard frequency. Okay, so we need to do some algebraic manipulation such that our frequency is equal to our angular frequency over 2 pi. As far as units go, this converts our radians per second, which is the units behind our angular frequency, into hertz. We have 2 pi radians down here. The radians in this variable cancel out with the radians in this conversion factor, so we have cycles per second, which is the definition of a hertz. Okay, so from here we need to calculate the angular frequency, and from the PRC we also know that omega is equal to our spring constant over our mass. And you might be wondering, hey sir, where did that come from? Well, I'll tell you. If you go back about a week or so from your math class, you may have seen, or you may have worked through solving a differential equation. Well, that's where it comes from. So let's lay it out. If you want to skip through this portion of the video, you can go straight to the course supplement for this lesson, and it goes through it step by step. Alright, so I'm going to do this work in blue to kind of separate it from the problem itself. So here we have a picture of our block. Notice that I've isolated my block. I've labeled all of the forces that are applied to our block, and those are the normal force, we have our weight force, and we have the force due to the spring. Now remember, at time 0, the block is passing through equilibrium and stretching out. So as it continues in the positive x direction, that spring force is going to point the opposite direction of displacement from equilibrium. So that's why I have the spring force pointing in that direction. At some other time, it could be pointing the other direction. But for this snapshot in time, we're going to keep it as is and continue on with our Newton's second law analysis of this specific situation. Alright, so I want you all to pause the video, and on your scratch piece of paper or your blank printout of the problem, I want you to do a Newton's second law analysis on this specific block. Now for the sanctity of time, I want you to just focus on the x direction. Alright, so how'd you do? Well, there's really only one force acting in the x direction, and it is our spring force. Now I have the negative sign here. That's the way it's listed in your PRC, but here it's there because my positive x direction is to the right, my force is pointing to the left. That's why it's there. Alright, so this negative sign is purely for direction purposes. Okay, so you have your left-hand side, which is dependent on the position, and you have the right side, which is the acceleration. And there's a connection between the acceleration and the position. What is it? It is the second time derivative of our position. So now you're starting to see that we have a differential equation such that we have, let me reformat it. So we have a second order, linear, homogeneous differential equation. Now if I take one more step and I format it such that when we take the second time derivative of our function x, we get back the original function times the negative of k, the spring constant, over the mass. Well, if we square something, i.e. we take the derivative, we get whatever's in the exponent down in front, but we do that twice, the only way we're going to end up with a negative sign in front is if we have the imaginary number up there, I. Well, our function could be an exponential with a negative I times some other, the time variable up in the exponent, which does work, but we do know for a fact that when you take two time derivatives of the sine function or two time derivatives of the cosine function, you get back your original trig function back with a negative sign in front, times the derivative of your time variable inside of your trig function. So that's going to be our best bet to go on. Let's assume that the form of our solution is going to be in terms of cosine or sine. So this is a generic solution to our differential equation. Now if we take two time derivatives of this function, then our variable omega comes down in front twice. Well, if that's the case, if we assume this is 1, our amplitude is 1, then the difference between this and our actual differential equation is omega squared. Well, if omega squared is whatever this is, k over m, then we can say that omega squared is equal to our spring constant over our mass. Therefore, our angular frequency is equal to the square root of our spring constant divided by our mass. So, a little long-winded, but that's where this equation comes from, and that's how we get at our position as a function of time of our simple harmonic oscillator. Now, switching gears back to our problem, we are given the mass and we are given the spring constant, so we can go straight to calculating omega and put it in terms of our frequency. So, of course, I refrain from putting in numbers until the absolute final end of the problem, or at least this part. So we would have the square root of k over m times 1 over 2 pi. Now I can do my calculation. My value comes out to 3.2 hertz. And that's two significant figures because that's what we're given here, here, and here. So if we think about the practicality of this answer, let's see, we've got a 1.2 kilogram block. That's probably about 2.5 pounds. Seems to be a pretty strong spring. So this is oscillating back and forth 3.2 times per second. Alright, so let's move on to part B. Part B of our problem is to calculate the amplitude of the block's motion. So from our last portion of, or for part A, especially in the blue ink, we pulled out our position as a function of time. Now from part A, we have our angular frequency. We know what the block is doing at time 0. It is at a position 0 and has a speed of 5.2 meters per second. What we want to find out here is our maximum amplitude, and we'll see if there's any effect of our phase constant in the final result. Now we have information on the position. How can we get from our position to an analytical way of describing the speed profile of our simple harmonic oscillator? Now that may sound a little complex, but what I'm trying to say is, if we have position information, how can we get velocity information? Well, there's a connection between our position and velocity, right? What's the relationship? It is what we have listed here. So our speed as a function of time is the first time derivative of our position function, which is dependent on time. Okay, so let's pause the video. I want you to execute this first time derivative of our position function. Alright, so how'd you do? Well, you should have gotten something along the lines of negative maximum amplitude times the derivative of the inside times sine of our original function, angular frequency times time plus our phase constant. Now, we know what's happening at time 0. We have a speed of 5.2 meters per second. We know what our angular frequency is from part A, and we're looking for the maximum amplitude. But there's a problem. We still don't know what this phase constant is. But let's see if we can pull it out just from a quick analysis of the total mechanical energy in the system as a function of time. So I'll do this in blue. We have our total mechanical energy is equal to our kinetic energy plus our potential energy. In this case, we have a spring and mass system, so our kinetic energy is in the form of translational kinetic energy, and our potential energy is in the form of spring potential energy. And that's what gets us our total mechanical energy. But now we have to think about how a spring and mass system oscillates. When it is at the fully compressed state or the fully stretched state, is it moving? Is it stationary? It's stationary. So if the maximum potential energy is at the point of full compression, then that is equal to our total mechanical energy. Because it's not moving, it's stationary, we don't have any translational kinetic energy. Well, what about the other extreme? Not necessarily the other end of stretching or compression, but as the block passes through the equilibrium point. Well, if the spring's in a relaxed state at equilibrium, do we have any spring potential energy? We do not. We have nothing but translational kinetic energy. So if our block is passing through equilibrium with a speed of 5.2 meters per second, then that has to be its maximum velocity, because that's going to be the point at which our translational kinetic energy is at a maximum and we have zero spring potential energy. Okay, with that quick analysis of total mechanical energy, we can look at our sinusoidal function that we have listed here. Well, if our speed at time 0 is at the equilibrium point, then what do we know about this sinusoidal term? Well, we know sine oscillates between -1 and 1 and back to -1 and so on and so forth. So at this point, if we have a maximum speed, then we must have a maximum here as well. And it just so happens that if we have a positive value but we have a negative in front, then this sine of omega t plus phi must be equal to -1. Oh, switch my colors. So sine of our angular frequency plus or times our time plus our phase constant, it must equal -1 in order to get our maximum speed at equilibrium. So if we know this is true at this instant in time, t is equal to 0, then our speed at time is equal to 0 is equal to -1 times our maximum displacement times our angular frequency. Now at this point we can isolate our variable where our maximum displacement is equal to the negative of the speed at time 0 divided by our angular frequency. And if we remember from part A, our angular frequency is equal to the square root of k over m. I'll put it up here for your reference. Now we can say our displacement, our maximum displacement is negative speed at time is equal to 0 times the mass over the spring constant. Now I kind of did some mental math in my head. Because omega is on the bottom, I brought it up to the numerator, but in doing so I needed to flip these two variables in order to be one continuous line there. Okay, so now once I put in my given values, I get a maximum amplitude of 0.26 meters or 26 centimeters. Alright, the final portion of our problem, part C, we need to write our position function out in its complete form. So here we have the generic form of our position of a simple harmonic oscillator, but we want to put in our values for the maximum amplitude, the angular frequency, and the phase constant. So far in part A we got our angular frequency, in part B we got our maximum amplitude. Now we need to pull out this phase constant and see what it actually is in order to write out our specific time-dependent position function for our simple harmonic oscillator. Alright, so remember from the last part we said that as the block is passing through the point of equilibrium at x is equal to 0, that our oscillating term was equal to -1. Well, not only is that true as it passes through equilibrium, but in our specific case, it was happening at t is equal to 0. So as we put in that information, we have the sine of phi is equal to -1. Well, we can do the arc sine of both sides such that we have the angle is equal to the arc sine of -1, and that comes out to be -pi/2. And we'd see it again 3pi/2, and then again at 7pi/2, and so on and so forth. We could even draw a fun little graph where we have our displacement in the x direction on the vertical axis, and we have our only variable here in this part of the problem. If we assume this is all happening at t is equal to 0, our horizontal axis is just our phase constant phi. So as we put that in, sine is always equal to 0 at phase is equal to 0, and from there it goes up and then down and then up and then down, and going backwards in phase, down, and so on and so forth. So here we have our displacement, and just as we can expect, here is our point negative pi over 2. Here's our point pi over 2. Here again is 3 pi over 2, and so on and so forth. But you see that when sine of phi is equal to negative 1, it is occurring at these points. So that's where that phase constant comes from. Generally, we want to get the smallest phase constant possible, so we will choose to go with our negative pi over 2. Oh, wrong color. So our phase constant is equal to negative pi over 2. Now let's put that into our generic position function. I want you to pause the video and put in our calculated values into the function itself and test how closely you're paying attention to the different variables. Alright, so how'd you do? Well, you may have, hopefully you noticed, that in order to fill out our generic position function, we had to pull from part A, but we don't pull in the frequency, we pull in the angular frequency. So first you had to do a quick calculation to get the angular frequency, which comes out to 20 radians per second. So as we fill this out, we have our maximum amplitude from part B. We can pull from our angular frequency, so part of the way into part A, to get our numeric value there, times a variable t, plus our phase constant, which was negative pi over 2. And that concludes not just part C, but the entire problem. Hopefully this will be useful for not only the WPR next week, but any potential problem sets and or just getting ready for class for lesson 22.